Assalamualaikum and hi, we are from Group 1 and today we will present about thermal cycling effect on jet turbine blade. So this is our group members, Haris, Ali Rizwan, Muizuddin and Ahmad Hakam.
Okay, for thermal cycling condition is refer to repeated and rapid change in temperature experienced by material due to alternating heating and cooling phase. In industrial application, these cycles can occur during operation, which is heating, and shutdown or standby, which is cooling. And each cycle imposes thermal stress on the material due to expansion during heating and contraction during cooling. For thermal cycling in jet turbine blade, we have two important points, which is high combustion temperature and cooling phase. For high combustion temperature, in the turbine section, blade encounter temperature exceeding 1500 degrees Celsius. So this is often above the melting point of the substrate material without protective coating. And second is cooling phase. During engine shutdown or reduced thrust condition, the blade cool rapidly. This cooling may occur multiple times over an engine operation life, depending on the frequency of operation. For the characteristic of coating for thermal cycling condition in jet turbine blade, the first characteristic for coating must have is thermal insulation. The coating must act as a barrier to reduce heat transfer to the blade for ensuring the internal material stay cooler and experience less stress from high temperature. This is important because we need to protect blade structural integrity and allow it to function in extreme temperature environment. Second is oxidation protection. In high temperature, will promote oxidation. Okay, high temperature environment will promote oxidation where the blade material react with oxygen and weaken over time. So the coating should prevent oxygen and other reactive element from reaching the blade surface and protecting it from weakening and degradation over time. So it's important to preserve the blade mechanical strength and prevent corrosion caused by long-term exposure to high temperature gas. The last is stress resistant. So thermal cycling will cause repeated expansion and contraction that lead to crack or separation of the coating from the blade. The coating must handle repeated expansion during heating and contraction during cooling caused by temperature change without cracking or separating from the blade surface. And a durable coating adapt to this stress, ensuring it remains intact and continues to provide protection over time.
Next, we will go to the coating material. The coating type is thermal barrier coating or known as TBC, which the common coating material is yttria stabilized zirconia or known as YSZ. Application method for the coating material is by plasma spraying and electron beam physical vapor deposition. Why SYZ? Because yttria stabilized zirconia is a type of ceramic coating which have crystalline structure which can reduce thermal conductivity by fusing yttria with zirconium dioxide that can enhance their thermal stability. It also by reducing thermal fatigue and prolonging component life. These are some of the advantages for yttria stabilized zirconia. First is enhanced protection from high temperature. Second, reduction in thermal stress on the substrate. Third, potential for higher engine efficiency. And the disadvantages are susceptibility to suspension due to thermal cycling. It also can make become less effective over time with prolonged exposure to extreme heat, and installation and repair can be complex and costly.
How to apply YSZ coating material onto the substrate? So we are using two techniques, which are plasma spraying and electron beam physical vapor deposition, which known as EBPVD. What is plasma spraying? Plasma spraying is a versatile process where a molten or semi-molten materials are sprayed onto the substrates, that resulting in a layered coating. While for EBPVD, can utilize a vacuum environment to deposit thin films and allowing for a strong bond and uniform coverage of the TBC. How does thermal spraying with YSZ work? It starts with a material preparation. YSZ powder is fed into a thermal spray gun, and then the powder is heated to a molten or semi-molten state using a heat source such as plasma torch, flame, or electric arc. And then we proceed with the propulsion process, which the molten particles are accelerated towards the substrate using a high velocity gas stream. Finally, the particle hit the substrates, flatten and rapidly solidify, and forming a dense and adherent coating. For the EBPVD working principle, it starts with the electron beam generation. A high energy electron beam is generated using an electron gun, and this beam is focused onto the target material such as YSZ. And then we continue with the vaporization process, which is the electron beam hits the target material to extremely high temperature that causing it to vaporize. And then the vaporized material travels through the vacuum chamber towards the substrate. Finally, the vapor condenses on the substrate, forming a thin, uniform coating, and the process is carefully controlled to achieve the desired thickness and microstructure.
Coating lifetime factors of TBC have two: operational condition and coating parameter. In operational condition, in terms of temperature, higher operational temperature can accelerate degradation and reduce TBC lifespan. While thermal cycling, repeated heating and cooling can induce thermal fatigue, leading to coating integrity issues. In coating parameter, affect thermal insulation and stress level. Thicker coating may provide better insulation but can lead to spallation. While bond coat properties, the characteristics of the bond coat, including its thickness and roughness, are critical for adhesion and performance. Coating lifetime model and methods prediction of TBC. Experimental testing. Isothermal furnace cyclic tests help establish empirical relationship between coating parameters and lifetime, while deep learning approaches, multi-scale deep learning method analyze microstructural damage to predict TBC failure under thermal shock. Turbine barrier coating have common failure. First is spallation, detachment of the ceramic layer from the bond coat due to thermal expansion, mismatch, and bond coat oxidation. While hot corrosion, electrochemical reaction leading to degradation, categorized into high temperature and low temperature types. Factors of failure in coating. First, erosion. Particular method can erode the protective ceramic layer, exposing the substrate to high temperature. Microstructural integrity. Defects or irregularities in the TBC microstructure can affect mechanical properties.
In conclusion, the study of thermocyclic effects on jet turbine blades highlights the critical role that temperature fluctuations play in the integrity and performance of this component. Continuous exposure to varying thermal conditions can lead to significant material degradation such as thermal fatigue, oxidation, and microstructural changes. These effects not only reduce the lifespan of the blades but also impact the overall efficiency and safety of jet engines. It is essential for ongoing research to focus on advanced materials and protective coatings that can withstand the harsh thermal environments encountered during operation. Implementing improved cooling techniques and rigorous maintenance protocol can further enhance the durability and reliability of turbine blades, ensuring optimum performance and safety in aerospace applications.